Out in the black silence of space, against the faint whisper of the cosmic background, scientists have stumbled upon something impossible. Etched across 13.8 billion light-years, rippling through the very skin of reality itself, lie patterns no one can explain. These are not random fluctuations. They are signatures, fingerprints left by something so vast, so incomprehensible, that it makes our entire visible cosmos seem like a single grain of sand on an infinite beach. We have always believed our universe was everything, the totality of existence. Every star, every galaxy, every particle of matter and energy contained within one cosmic bubble stretching from the Big Bang to the heat death of time. But what if we were wrong? What if our universe, with its precisely tuned laws of physics, its perfect balance of forces that allow stars to shine and life to flourish, is just one of infinite realities? What if beyond the edge of everything we can see, beyond the cosmic horizon that marks the boundary of our observable reality, there exist countless other universes with different laws, different histories, different possibilities? Today, we journey through evidence that challenges the very foundation of our understanding. We will explore quantum fluctuations that birth entire realities, examine cosmic patterns that hint at collisions between universes, and investigate why the most brilliant minds in physics have concluded that infinity is not just possible, it is inevitable. We will discover how the mathematics that govern the smallest particles also predict the existence of the largest structures imaginable. And we will learn why the multiverse is not just a fantasy of science fiction, but an inescapable consequence of the physics we observe every day. Long before modern telescopes peered into the cosmic depths, long before quantum mechanics revealed the strange nature of reality, ancient minds grappled with a profound question. Could there be worlds beyond our own? The idea of multiple universes is not a modern invention. It stretches back over 2,000 years to the earliest philosophers who dared to imagine infinity. In the bustling agoras of ancient Greece, around the 3rd century before Christ, a revolutionary idea was taking shape. The atomists, philosophers like Democritus and Epicurus, proposed that all of reality consisted of tiny, indivisible particles called atoms moving through infinite void. But their vision extended far beyond our single world. Democritus declared that infinite atoms colliding in infinite space would inevitably create not just one world, but countless worlds. There are infinite worlds both like and unlike this world of ours, he wrote. These ancient thinkers understood that if space and matter were infinite, then every possible combination of atoms must occur somewhere, creating worlds upon worlds in an endless cosmic dance. The philosopher Chrysippus pushed this concept even further, suggesting that our world eternally expires and regenerates in endless cycles. He envisioned time itself as infinite, with our universe dying and being reborn countless times, each cycle potentially bringing forth slightly different realities. This was perhaps the first glimpse of what we now call the cyclic multiverse. But these weren't just philosophical flights of fancy. The atomists built their multiverse theories on logical foundations that remain valid today. If atoms are finite in variety but infinite in number, and if space extends without limit, then mathematical necessity demands that every possible arrangement of matter must occur infinitely many times across the cosmic expanse. Even more remarkably, some ancient thinkers anticipated modern ideas about parallel versions of ourselves. The atomist Metrodorus of Chios wrote, "It would be strange if a single ear of corn grew in a large plain, or there were only one world in the infinite." He understood that in infinite space with infinite matter, not only would there be other worlds, but there would be worlds exactly like ours, with exact copies of every person who ever lived. This ancient insight predates by over 2 millennia of our modern understanding of the Level 1 multiverse, the idea that in infinite space, there must be regions identical to our observable universe. The atomists arrived at this conclusion through pure logic, without telescopes, without knowledge of galaxies or cosmic expansion, simply by reasoning about the nature of infinity. The Indian philosophical traditions also grappled with multiverse concepts. Ancient Hindu and Buddhist cosmologies described vast cycles of creation and destruction, with countless worlds existing across multiple dimensions of reality. The Puranas speak of infinite universes, each with its own gods, laws, and destinies, all arising and dissolving in eternal cosmic rhythms. These ancient multiverse concepts weren't dismissed as mythology. They were taken seriously by some of the greatest minds in history. The Roman poet Lucretius, in his epic On the Nature of Things, eloquently defended atomist multiverse theories. Nothing in the universe is unique and alone, and therefore in other regions there must be other Earths inhabited by different tribes of men and breeds of beasts. But perhaps the most profound ancient insight came from the recognition that infinite worlds would contain infinite possibilities. If every arrangement of atoms occurs somewhere in the multiverse, then there must be worlds where history unfolded differently, where different choices were made, where different outcomes emerged from the chaos of cosmic evolution. The atomists understood that their multiverse theories had profound implications for human existence and meaning. If infinite copies of ourselves exist across parallel worlds, what makes any particular life special? How do we think about fate and choice when every possible path is realized somewhere in the cosmic infinity? These questions troubled ancient minds just as they challenge us today. Some found comfort in the idea that death was not final, that other versions of ourselves continued in parallel realities. Others found the infinite multiverse overwhelming, a cosmic vastness that dwarfed human significance and purpose. Interestingly, ancient multiverse theories were often rejected not on scientific grounds, but for their perceived threat to human meaning and divine purpose. Aristotle, despite his towering intellect, dismissed the possibility of multiple worlds partly because he believed it would undermine the special significance of Earth and humanity. The medieval period saw multiverse ideas largely suppressed in the Western world, as religious orthodoxy demanded a single, divinely created universe with Earth at its center. But the ideas never completely disappeared. Islamic philosophers like Al-Ghazali and Averroes continued to explore the possibility of multiple worlds, keeping alive the ancient spark of infinite imagination. The Renaissance brought renewed interest in atomist theories and multiverse possibilities. Giordano Bruno, the radical monk philosopher, not only championed the idea of infinite worlds but paid for his beliefs with his life when he was burned at the stake in 1600. Bruno envisioned countless stars with their own planetary systems, each potentially harboring life and consciousness. Bruno's vision was remarkably prescient. He understood that the universe revealed by Copernicus and Galileo, with Earth no longer at the center, naturally led to questions about other worlds and other possibilities. If our world was not unique in space, why should it be unique in the vast cosmos of possibilities? What's striking about these ancient and historical multiverse theories is how closely they parallel modern scientific concepts. The atomist idea of infinite matter in infinite space creating infinite worlds directly corresponds to our Level 1 multiverse. The cyclic universe concepts of Chrysippus and ancient Indian philosophy echo modern ideas about eternal inflation and universe reproduction. The ancient recognition that infinite worlds would contain infinite copies of ourselves anticipated modern quantum mechanical ideas about parallel versions of consciousness across the many worlds multiverse. Even the ancient understanding that multiverse theories challenge human meaning and significance remains relevant to contemporary debates about anthropic reasoning and cosmic purpose. But the ancients lacked one crucial element that we possess today: empirical evidence. Their multiverse theories, however brilliant, remained in the realm of philosophical speculation. They could reason about infinity and possibility, but they couldn't peer into the cosmic microwave background or detect gravitational waves from universe collisions. This is what makes our current era so extraordinary. We are the first generation in human history that might actually be able to prove what ancient minds could only imagine. The multiverse concepts that inspired philosophers for over 2 millennia may finally be within reach of experimental verification. As we now turn to examine the modern evidence for parallel universes, we carry with us this ancient legacy of wonder and questioning. The multiverse is not just a recent scientific hypothesis. It is the culmination of humanity's longest-running intellectual adventure, a quest that began in ancient Greek marketplaces and may reach its conclusion in the data streams of 21st century telescopes. The ancients gave us the vision. Modern science may give us the proof. In the beginning, there was nothing. Not empty space, not darkness, not time itself, simply nothing. Then, in an instant so brief it defies human comprehension, everything exploded into existence. The Big Bang. But here's what most people don't realize about this cosmic genesis. It wasn't just the birth of our universe. It was the moment when the infinite became possible, fulfilling the ancient vision of countless worlds that philosophers had dreamed of for millennia. Picture this: 13.8 billion years ago, our entire observable universe, every star, every planet, every atom in your body, was compressed into a region smaller than the period at the end of this sentence. The temperature was infinite. The density was infinite. The laws of physics as we know them did not exist. This was what physicists call a singularity, a point where our mathematics breaks down and our understanding reaches its limits. But something miraculous happened in those first moments. Through a process we now call cosmic inflation, space itself began to expand at a rate that beggars the imagination. Not just fast, faster than the speed of light. In less time than it takes light to travel the width of a proton, our universe grew from subatomic to astronomical in size. This period of inflation lasted for only a fraction of a second, but it set the stage for everything that would follow. Now, here's where it gets interesting. The theory of cosmic inflation, developed by physicist Alan Guth in the 1980s, doesn't just explain how our universe came to be. It predicts that inflation didn't happen just once, in just one place. Instead, it suggests that inflation is an ongoing process, happening constantly throughout a vast cosmic landscape we can barely imagine. Think of it this way: imagine you're blowing soap bubbles. Each bubble represents a universe. As you blow, more and more bubbles form, each one expanding rapidly as it's created. Some bubbles are large, some small. Some last longer than others before they pop. But the process of bubble creation never stops. This is eternal inflation, and it's the first major piece of evidence that our universe is not alone. Dr. Andre Linde, one of the founding fathers of inflation theory, describes it like this: inflation creates a fractal structure of universes, where each region that stops inflating becomes a new cosmic bubble, while other regions continue to inflate and spawn more bubbles. It's a cosmic reproduction process that has been going on for eternity and will continue forever. But why should we believe this isn't just mathematical speculation? The answer lies in the cosmic microwave background, the afterglow of the Big Bang that permeates all of space. When we map this radiation with satellites like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, we see tiny fluctuations in temperature across the sky. These fluctuations are the seeds that grew into galaxies and galaxy clusters. But their pattern, their statistical distribution, matches exactly what inflation theory predicts. More remarkably, these measurements have revealed something unexpected. The fluctuations aren't completely random. There are subtle patterns, correlations across vast distances that suggest our observable universe might have interacted with something else during its earliest moments. Some scientists interpret these patterns as evidence of collision with other universe bubbles during the inflationary period. The mathematics of inflation theory also predict something profound about the nature of these bubble universes. Due to quantum fluctuations during the inflationary period, each bubble universe would have slightly different properties. The fundamental constants of physics, things like the strength of gravity, the charge of the electron, the mass of the proton, could vary from universe to universe. This leads to a staggering conclusion. If inflation theory is correct, then not only are there infinite universes, but there are infinite universes with every possible combination of physical laws. There would be universes where gravity is stronger, making stars burn out quickly and planets impossible to form. There would be universes where the electromagnetic force is weaker, making atoms unstable and chemistry impossible. And there would be universes with just the right combination of forces to allow for complexity, life, and consciousness, universes like ours. The beauty of this theory is that it explains one of the most puzzling aspects of our reality: why the universe seems so perfectly fine-tuned for life. The fundamental constants of physics appear to be calibrated with extraordinary precision to allow for the existence of stars, planets, and biological processes. Change any of these constants by even a small amount, and the universe becomes hostile to life. This fine-tuning has long puzzled scientists and philosophers. Some see it as evidence for intelligent design. Others propose the anthropic principle, the idea that we observe a life-friendly universe simply because we exist to observe it. But the multiverse provides an elegant third option. If there are infinite universes with all possible values of these constants, then it's not surprising that some universes would be life-friendly. We find ourselves in one of these universes not because it was designed for us, but because universes that can't support life have no one to observe them. This is where the science becomes almost philosophical in its implications. If the multiverse exists, then every possible history, every possible outcome, every possible version of reality exists somewhere. There would be universes where the dinosaurs never went extinct, universes where Earth never formed, universes where the laws of physics are so different that matter as we know it cannot exist. But inflation theory is just the beginning. The deeper we dig into the foundations of reality, the more evidence we find that our universe is part of something much larger and more extraordinary than we ever imagined. To understand why the multiverse might be inevitable, we need to journey into the quantum realm, the strange, counterintuitive world that governs the behavior of the smallest particles in existence. Here, in the space between spaces, reality behaves in ways that challenge our most basic assumptions about how the world works. In 1926, Austrian physicist Erwin Schrödinger developed an equation that would revolutionize our understanding of reality. Schrödinger's equation describes how quantum systems evolve over time, and it has one very peculiar property. It allows particles to exist in multiple states simultaneously, a phenomenon called superposition. The most famous illustration of this concept is Schrödinger's thought experiment about a cat in a box. According to quantum mechanics, before we open the box to look, the cat exists in a superposition of being both alive and dead. It's only when we make an observation that the wave function collapses and the cat becomes definitely alive or definitely dead. This seems absurd, and Schrödinger himself was troubled by the implications of his own equation. But the mathematics is unambiguous, and countless experiments have confirmed that particles do indeed exist in superposition until they are observed or measured. Now, here's where it gets even stranger. In 1957, a graduate student at Princeton University named Hugh Everett III proposed a radical solution to the measurement problem in quantum mechanics. Instead of wave function collapse, Everett suggested that all possible outcomes of a quantum measurement actually occur, but in separate parallel realities. This is the many worlds interpretation of quantum mechanics, and it suggests that every time a quantum event occurs, the universe splits into multiple branches, each representing a different possible outcome. If this interpretation is correct, then at every moment, countless versions of yourself are being created across an infinite number of parallel universes. Think about it this way. Right now, as you listen to these words, quantum events are occurring in your brain and throughout your body. Electrons are jumping between energy levels, radioactive atoms are decaying, chemical reactions are proceeding according to quantum probabilities. According to the many worlds interpretation, each of these quantum events creates a branching point where the universe splits into multiple copies, each with a slightly different outcome. The implications are mind-boggling. There would be universes where you decided to listen to something else instead of this video. Universes where you were never born. Universes where history unfolded differently because of different quantum outcomes in the brains of key historical figures. Every possible variation of reality that is consistent with the laws of physics would exist somewhere in the vast multiverse of quantum possibilities. But the many worlds interpretation isn't just philosophical speculation. It has practical implications for our understanding of physics. Many of the strange phenomena of quantum mechanics, like quantum entanglement and quantum tunneling, make more sense when viewed through the lens of multiple realities. Consider quantum tunneling, where particles can pass through barriers that should be impossible to cross according to classical physics. In the many worlds interpretation, the particle doesn't tunnel through the barrier. Instead, in some branches of reality, the particle reflects off the barrier, while in others it appears on the other side. From our perspective in any single branch, it appears as if the particle has tunneled through, but actually the multiverse has split to accommodate both possibilities. The evidence for quantum mechanics is overwhelming. Every modern technology, from lasers to computer chips to MRI machines, depends on quantum effects. The GPS satellites that help you navigate rely on quantum clocks that tick according to quantum mechanics. The internet itself runs on quantum-based semiconductor technology, and quantum mechanics unambiguously predicts superposition. We've observed it in individual photons, electrons, and even large molecules. In 2019, scientists achieved superposition with objects containing trillions of atoms. The quantum realm isn't just theoretical, it's the foundation of our technological civilization. But if superposition is real, and if the many worlds interpretation is correct, then the multiverse isn't optional. It's a necessary consequence of the fundamental laws that govern reality. The quantum multiverse would be vast beyond imagination. Every quantum event, everywhere in the universe, at every moment in time, would create branching realities. The number of parallel universes would grow exponentially with each passing instant. Some physicists estimate that the quantum multiverse splits into 10 to the 10th to the 50th power new branches every second. This raises profound questions about the nature of identity and consciousness. If there are countless versions of you across the quantum multiverse, which one is the real you? The answer, according to the many worlds interpretation, is that they all are. Each branch of the multiverse is equally real and equally valid. Some versions of you might have made different life choices, leading to entirely different careers, relationships, and experiences. Other versions might be so similar to you that the only differences lie in quantum events that have no macroscopic consequences. and some versions might be so different, due to different quantum outcomes in the distant past, that they would be unrecognizable as the same person. This quantum perspective on the multiverse connects deeply with the inflationary multiverse we discussed earlier. Both suggest that reality is far larger and more complex than our single observable universe. Both arise from well-tested physical theories rather than pure speculation. And both have implications that challenge our understanding of existence itself. But the quantum realm offers us more than just theoretical predictions about parallel universes. It provides us with experimental tools to probe the nature of reality in ways that were impossible just a few decades ago. The search for evidence of the multiverse presents a unique challenge in science. How do you prove the existence of something that, by definition, lies beyond the bounds of our observable reality? The answer lies in looking for subtle signatures, cosmic fingerprints left by the interaction between our universe and its neighbors in the vast multiverse. The first place scientists looked for these signatures was in the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. This radiation carries within it a detailed map of the early universe, showing us what conditions were like when the cosmos was only 300,000 years old. In 2010, a team of scientists led by Stephen Feeney at University College London announced that they had found something extraordinary in the CMB data. Using information from the Wilkinson microwave anisotropy probe, they identified circular patterns in the radiation that could be explained by collisions between our universe bubble and other universe bubbles during the inflationary period. These cosmic bruises, as they came to be called, appeared as disc-shaped regions where the temperature of the cosmic microwave background was different from the surrounding areas. The patterns matched theoretical predictions for what would happen if our expanding universe bubble collided with another expanding universe bubble in the early cosmos. The discovery made headlines around the world. Here, potentially, was the first direct evidence that our universe was not alone. But science is a process of verification and peer review, and other teams of scientists began to scrutinize the claimed evidence. When the European Space Agency's Planck satellite produced even more detailed maps of the cosmic microwave background, the results were mixed. Some of the circular patterns identified by Feeney's team could not be confirmed with the higher resolution data. However, this doesn't necessarily disprove the multiverse. It might simply mean that the signatures are more subtle than initially thought, or that our universe has not experienced any recent collisions with other universes. But the search for multiverse evidence goes beyond looking for cosmic bruises. Scientists have developed other techniques to probe the possibility that our universe is part of a larger multiverse. One approach involves looking for evidence of gravitational effects from other universes. Just as the moon's gravity affects the tides on Earth, the gravity from nearby parallel universes might create detectable effects in our cosmos. These effects would be incredibly subtle, but advances in gravitational wave detection might eventually make them observable. The LIGO and Virgo gravitational wave observatories, which have already detected ripples in spacetime caused by colliding black holes and neutron stars, represent a new window into the cosmos. Future generations of these instruments might be sensitive enough to detect the gravitational influence of other universes. Another line of evidence comes from studying the fundamental constants of physics themselves. If our universe is part of a multiverse where these constants can vary, we might expect to see slight variations in their values across different regions of our observable universe. Some scientists have claimed to find evidence for such variations. In 2010, a team led by John Webb at the University of New South Wales reported that the fine structure constant, which determines the strength of electromagnetic interactions, appeared to have different values when measured in opposite directions across the sky. If confirmed, This would suggest that our universe is part of a larger structure where physical laws can vary. However, like many claims about multiverse evidence, these results remain controversial. Other teams have failed to reproduce the findings, and systematic errors in the measurements remain a possibility. The search for varying constants continues, with new telescopes and more precise measurement techniques offering hope for definitive answers. Perhaps the most intriguing evidence for the multiverse comes from quantum mechanics experiments themselves. In recent years, scientists have developed increasingly sophisticated ways to test the predictions of quantum mechanics and explore the implications of superposition and entanglement. One particularly relevant experiment involves quantum interference effects. When particles exist in superposition, they can interfere with themselves, creating patterns that reveal information about all possible paths the particle could have taken. Some interpretations of these experiments suggest that the interfering particles are actually interacting with versions of themselves in parallel universes. The double-slit experiment, where particles behave differently depending on whether they are observed, has been refined and extended in ways that probe deeper into the quantum realm. In some versions of the experiment, scientists have found interference patterns that seem to require the existence of shadow photons, particles that interact with our photons but exist in parallel realities. While these experiments don't prove the existence of parallel universes, they are consistent with multiverse theories and difficult to explain using purely single-universe models of quantum mechanics. Another area where evidence for the multiverse might be found is in the study of dark matter and dark energy. These mysterious components make up 95% of our universe, but their nature remains unknown. Some theories suggest that dark matter might be ordinary matter existing in parallel dimensions that weakly interact with our own. If this is correct, then the gravitational effects we attribute to dark matter might actually be the gravitational influence of matter in nearby parallel universes. This would mean that the evidence for dark matter is actually evidence for the multiverse. The invisible mass we detect through its gravitational effects is simply matter that exists in dimensions parallel to our own. Similarly, dark energy, the mysterious force causing the accelerated expansion of our universe, might be explained by the pressure exerted by other universes in the multiverse. Just as air molecules in a balloon exert pressure that keeps the balloon inflated, other universes might exert pressure that drives the accelerated expansion of our own cosmos. These ideas remain highly speculative, but they illustrate how multiverse theories can potentially explain some of the deepest mysteries in cosmology. As our understanding of dark matter and dark energy improves, we may find that their properties point toward a multiverse origin. The search for multiverse evidence also extends to the study of black holes. Some theories suggest that black holes might be portals to other universes, or that the information that falls into black holes might be preserved in parallel realities. The recent breakthroughs in black hole imaging and gravitational wave detection from black hole mergers provide new ways to test these ideas. Stephen Hawking's work on black hole thermodynamics led to the black hole information paradox, the question of what happens to information that falls into a black hole. Some solutions to this paradox invoke the multiverse, suggesting that information is preserved across multiple realities even if it seems to disappear from our own universe. To truly understand why leading physicists believe in the multiverse, we need to dive into the mathematics that govern reality at its most fundamental level. These equations don't just suggest that multiple universes are possible, they indicate that infinite universes are inevitable. Let's start with the mathematics of cosmic inflation. The key insight is that inflation is not a one-time event, but an ongoing process that creates a fractal structure of universes. The mathematical description of this process involves exponential growth rates that quickly lead to infinite quantities. During the inflationary period, space expands exponentially. This means that the size of the inflating region doubles in a fixed amount of time, then doubles again in the same amount of time, and so on. Mathematically, we can represent this as a function where the size grows as e to the power of ht, where h is the Hubble parameter during inflation and t is time. But here's the crucial point. While inflation ends in some regions, creating universe bubbles like ours, it continues forever in other regions. The mathematics shows that the volume of space that is still inflating grows faster than the volume of space where inflation has ended. This leads to eternal inflation, a process that creates an infinite number of universe bubbles. Max Tegmark, a physicist at MIT, has developed a comprehensive mathematical framework for classifying different types of multiverses. His level for multiverse, the ultimate ensemble, is based on a profound mathematical insight that physical existence and mathematical existence might be the same thing. The mathematical universe hypothesis proposes that our physical reality is a mathematical structure. Not that it's described by mathematics, but that it literally is mathematics. If this is correct, then every mathematically consistent structure corresponds to a physical reality somewhere in the ultimate multiverse. This idea might sound abstract, but it has concrete implications. The laws of physics in our universe can be expressed as mathematical relationships. Einstein's field equations, Schrödinger's equation, Maxwell's equations for electromagnetism. These aren't just descriptions of reality. According to Tegmark, they are reality. If the mathematical universe hypothesis is correct, then every possible mathematical structure that could describe a consistent universe actually exists as a physical universe. This would include universes with different numbers of spatial dimensions, different symmetries, different fundamental particles and forces. The mathematics also tells us something important about the quantum multiverse. In quantum field theory, the equations naturally predict the existence of superposition states. When we solve Schrödinger's equation for a quantum system, we get a wave function that describes all possible states of the system simultaneously. The mathematical formalism of quantum mechanics doesn't single out any particular measurement outcome as special. Instead, it treats all possible outcomes equally. This is what led Everett to propose the many worlds interpretation. The mathematics itself suggests that all possibilities are realized. But perhaps the most compelling mathematical argument for the multiverse comes from the theory of eternal inflation combined with quantum mechanics. The equations predict that quantum fluctuations during inflation will create regions with slightly different physical properties. Over infinite time and infinite space, these fluctuations will produce every possible combination of physical laws and initial conditions. André Linde, one of the architects of inflation theory, puts it this way: in the context of inflation, our universe is not just one of many possible universes, but one of infinitely many actually existing universes. Each of these universes has its own laws of physics, its own history, and its own future. The mathematics also provides insights into the structure of the multiverse. Different regions of the multiverse would be causally disconnected from each other. No information or influence can travel from one universe to another because space itself expands too rapidly between them. This causal disconnection has profound implications. It means that each universe in the multiverse evolves independently, following its own physical laws without interference from its neighbors. It also means that the multiverse as a whole has no definite size or age. It simply is, existing as an eternal, infinite structure of causally disconnected regions. The mathematical consistency of multiverse theories is remarkable. When physicists work out the equations, they find that the multiverse naturally solves many of the puzzles that plague single-universe cosmology. The fine-tuning problem, the horizon problem, the flatness problem, all of these are resolved when we consider our universe as part of a larger multiverse. consider the fine-tuning problem in detail. The fundamental constants of physics appear to be calibrated with extraordinary precision to allow for the existence of complexity and life. The ratio of the electron mass to the proton mass, the strength of the nuclear forces relative to gravity, the rate of expansion of the universe. Change any of these by more than a few percent and stars can't form, atoms become unstable, or the universe expands too rapidly for galaxies to condense. In a single universe, this fine-tuning seems to require either extraordinary luck or intelligent design. But in a multiverse with infinite variations, fine-tuning becomes inevitable. With infinite universes exploring all possible values of the fundamental constants, some universes will inevitably have the right combination for complexity and life. The mathematics of probability makes this clear. If there are infinite universes with randomly distributed physical constants, then the probability of at least one universe having life-friendly constants approaches 1. That is, it becomes virtually certain. But the mathematical argument goes deeper than just probability. The equations of quantum mechanics and general relativity, when combined, seem to naturally generate multiverse structures. It's not that physicists decided to add parallel universes to their theories. The mathematics forced the multiverse upon them. This is why so many leading physicists now take the multiverse seriously. It's not based on speculation or wishful thinking, but on the logical consequences of our best mathematical theories of reality. The mathematics also suggests that the multiverse has a hierarchical structure. At the smallest scale, quantum mechanics creates the many worlds multiverse, where every quantum measurement splits reality into multiple branches. At larger scales, eternal inflation creates bubble universes with different physical laws. At the largest scales, the mathematical universe hypothesis suggests that all possible mathematical structures exist as physical realities. This hierarchical structure means that the full multiverse is almost incomprehensibly vast. Not only are there infinite versions of you making different choices in the quantum multiverse, but there are also infinite versions living in universes with entirely different physics, and infinite versions existing as part of completely alien mathematical structures. The mathematics of infinity itself becomes relevant here. Different types of infinity have different sizes. Some infinities are larger than others. The multiverse likely contains multiple levels of infinity, each vast beyond human comprehension. The question of whether the multiverse is real has created one of the most significant debates in modern physics. On one side stand scientists who argue that multiverse theories are a natural and inevitable consequence of our best physical theories. On the other side are those who contend that untestable hypotheses about parallel universes represent a departure from the scientific method itself. The debate began in earnest in the 1980s, as cosmic inflation theory gained acceptance among cosmologists. The theory explained many puzzling features of our observable universe: why space appears to be flat, why the cosmic microwave background has such uniform temperature, why certain theoretical particles have never been observed. But inflation theory came with an unwelcome consequence. If the theory was correct, it seemed to predict the existence of countless other universes beyond our own. Many physicists were uncomfortable with this implication. How could science make claims about realms that could never be observed or tested? Alan Guth, who developed the original inflation theory, initially tried to avoid the multiverse implications of his work. But as the mathematics was refined by Andrei Linde, Alex Vilenkin, and others, it became clear that eternal inflation, and therefore the multiverse, was not an optional add-on to the theory but an inescapable consequence. Today, most cosmologists accept inflation theory, and many have come to embrace its multiverse implications. A survey of cosmologists conducted in 2019 found that roughly 60% believed that the multiverse was either likely or very likely to exist. Among the prominent supporters of multiverse theories is Brian Greene, a theoretical physicist at Columbia University and popular science author. In his books and lectures, Greene argues that the multiverse is not a speculative add-on to physics, but a natural consequence of string theory, quantum mechanics, and cosmology. The multiverse is not something we want to be true, Greene explains. It's something that emerges from the mathematics whether we like it or not. Our job as scientists is to follow the equations wherever they lead, even if the destination makes us uncomfortable. Similarly, Max Tegmark has become one of the most vocal advocates for taking the multiverse seriously. His mathematical universe hypothesis represents the most radical version of multiverse theory, suggesting that every mathematically consistent structure exists as a physical reality. Tegmark argues that the multiverse resolves many of the puzzles that have long troubled physicists and philosophers. The multiverse explains why the fundamental constants appear fine-tuned for life, why quantum mechanics seems to require an observer to collapse the wave function, and why the universe appears to have such a remarkable mathematical structure, he says. But not all physicists are convinced. The opposition to multiverse theories is led by some equally distinguished scientists who argue that the concept represents a dangerous departure from empirical science. Paul Steinhardt, a cosmologist at Princeton University, has been one of the most vocal critics of multiverse theories. He argues that the multiverse hypothesis is unfalsifiable. It makes no testable predictions and therefore falls outside the realm of science. A theory that can explain anything explains nothing, Steinhardt argues. If we allow ourselves to invoke infinite parallel universes to explain away any inconvenient observation, we abandon the self-correcting mechanism that has made science so successful. Steinhardt and other critics worry that accepting the multiverse will lead to a slippery slope where physicists abandon the requirement that theories make testable predictions. They point out that throughout the history of science, the most successful theories have been those that could be definitively proven wrong by experiment. Another prominent critic is George Ellis, a cosmologist at the University of Cape Town who has worked extensively on general relativity and cosmology. Ellis argues that the multiverse represents a fundamental misunderstanding of what science can and should attempt to do. Science is about understanding the world we can observe, Ellis contends. When we start making claims about realms that are in principle unobservable, we're no longer doing science, we're doing metaphysics. The debate has sometimes become heated, with both sides accusing the other of abandoning scientific principles. Critics argue that multiverse proponents are guilty of wishful thinking, allowing their desire for elegant mathematical theories to override their commitment to empirical evidence. Supporters counter that critics are being unnecessarily conservative, refusing to accept the logical implications of well-tested theories. The controversy has practical implications for the direction of physics research. Funding agencies must decide whether to support research programs based on multiverse theories. Universities must choose which approaches to emphasize in their physics curricula. Students entering physics must decide which research programs offer the best prospects for advancing human knowledge. Adding complexity to the debate is the fact that different multiverse theories have different levels of testability. The many worlds interpretation of quantum mechanics makes specific predictions about quantum interference effects that can, in principle, be tested experimentally. The inflationary multiverse makes predictions about patterns in the cosmic microwave background that we can observe with satellites. But other versions of the multiverse, particularly Tegmark's Level 4 mathematical multiverse, seem to be completely beyond observational reach. This has led some physicists to adopt a nuanced position, accepting some forms of multiverse theory while rejecting others. Nobel laureate Steven Weinberg has taken such a middle position. He accepts the inflationary multiverse as a natural consequence of our best cosmological theories, but remains skeptical of more speculative versions of the multiverse hypothesis. The multiverse arising from eternal inflation seems to be forced upon us by the mathematics of general relativity and quantum field theory, Weinberg argues. But we should be careful not to extend the concept beyond what the physics actually requires. The debate has also revealed deeper philosophical divisions within the physics community about the nature and goals of science. Some physicists see their role as discovering mathematical truths about the structure of reality, even if those truths concern unobservable realms. Others believe that science should focus exclusively on making predictions about observable phenomena. This philosophical divide affects how physicists interpret quantum mechanics, evaluate cosmological theories, and think about the relationship between mathematics and physical reality. It reflects competing visions of what physics should aspire to achieve. Recent developments have added new dimensions to the debate. The discovery of gravitational waves has opened new observational windows that might eventually detect multiverse signatures. Advances in quantum computing might allow more sophisticated tests of quantum mechanics interpretations. Meanwhile, improvements in cosmic microwave background observations continue to search for the subtle patterns that might reveal evidence of other universes. Each new dataset brings the possibility of settling the multiverse question once and for all. The debate within the physics community reflects the revolutionary nature of multiverse theories. If correct, these theories would fundamentally change our understanding of reality, consciousness, and our place in the cosmos. Such profound implications naturally generate strong reactions from scientists who have dedicated their careers to understanding the universe. One of the most important concepts for understanding the multiverse is the idea of cosmic horizons, the boundaries that define what we can possibly observe from our location in space and time. These horizons don't just limit our current observations. They represent fundamental limits imposed by the nature of space-time itself. The most familiar cosmic horizon is our observable universe boundary, located approximately 46 billion light-years away in all directions. This might seem contradictory at first. If the universe is only 13.8 billion years old, how can we see objects that are 46 billion light-years away? The answer lies in the expansion of space itself. Light from distant objects has been traveling toward us for billions of years, but during that time, space has been expanding, stretching the distance between us and those objects. The cosmic microwave background radiation, for example, was emitted when the universe was only 300,000 years old. But the objects that emitted this radiation are now about 46 billion light-years away due to cosmic expansion. This observable universe boundary is not a physical edge. It's simply the limit of what we can possibly see given the age of the universe and the speed of light. Beyond this horizon, there may be more galaxies, more stars, more planets, but their light has not had enough time to reach us since the beginning of the universe. But here's where it gets interesting from a multiverse perspective. There's no reason to think that space ends at our observable horizon. In fact, all evidence suggests that space extends far beyond what we can see. The geometry of space appears to be flat, which in cosmology implies that space could be infinite in extent. If space is indeed infinite, then our observable universe is just one small patch of a vastly larger cosmos. And if the laws of physics are the same everywhere, then this larger cosmos should contain an infinite number of regions similar to our observable universe. This leads to what cosmologists call the level 1 multiverse. In an infinite universe with finite age, there would be infinitely many regions like our observable universe, each containing its own collection of galaxies, stars, and planets. Since there are only finitely many ways to arrange matter within any given region, these distant domains would eventually repeat every possible configuration. The implications are staggering. If the level 1 multiverse exists, then there would be infinitely many planets exactly like Earth, with infinitely many copies of every person who has ever lived. There would be regions where history unfolded differently, where the dinosaurs never went extinct, where World War II ended differently, where you made different life choices. The distance to these duplicate regions depends on the entropy of our observable universe. Essentially, how many different ways the matter and energy within it can be arranged. Cosmologists estimate that an exact duplicate of our observable universe should appear approximately every 10 to the 10 to the 115th power meters away. That's a distance so vast it defies human comprehension. But in an infinite universe, such duplicates are not just possible but inevitable. But our cosmic horizon is not just defined by the observable universe boundary. There are other horizons that impose different limits on what we can possibly know or influence. The particle horizon defines the boundary of regions that could ever have communicated with us since the beginning of the universe. Due to cosmic expansion, this horizon is slightly different from the observable universe boundary, but the basic concept is the same. It represents the limit of causal connectivity in our cosmic neighborhood. Even more important for multiverse theories is the event horizon, which defines the boundary of regions that we could ever possibly influence, even if we wait forever. Due to the accelerating expansion of the universe caused by dark energy, distant galaxies are moving away from us at ever-increasing speeds. Eventually, galaxies beyond a certain distance will be receding so rapidly that no signal we send today could ever reach them. This event horizon is currently located about 16 billion light-years away. Galaxies beyond this distance are already causally disconnected from us. We will never be able to communicate with them, no matter how long we wait or how advanced our technology becomes. The existence of these cosmic horizons is crucial for understanding why multiverse theories are scientifically meaningful even though they involve unobservable realms. The horizons show us that our universe already contains regions that we can never observe or influence, yet we don't doubt their existence. Consider the cosmic microwave background radiation. This ancient light shows us the universe as it existed when it was only 300,000 years old. But the objects that emitted this radiation are now so far away that they lie beyond our event horizon. We can see their past, but we can never interact with their present. This raises a profound question. If we accept the existence of regions beyond our cosmic horizons based on extrapolating known physics, why should we reject the possibility of other universes that are also beyond observation? The mathematics of cosmic expansion provides another perspective on multiverse possibilities. During the inflationary period, space expanded faster than light, creating regions that were causally disconnected from the very beginning. These regions would have evolved independently, following the same laws of physics but starting with different initial conditions determined by quantum fluctuations. From our perspective, these causally disconnected regions are indistinguishable from separate universes. They have their own galaxies, their own planets, potentially their own forms of life. We can never communicate with them or visit them, but their existence follows naturally from the same physics that describes our own cosmic neighborhood. The concept of cosmic horizons also helps us understand the structure of the inflationary multiverse. Each bubble universe created during eternal inflation has its own set of horizons, defining what observers within that universe can possibly see or influence. These bubble universes exist in the same overall spacetime, but they are causally isolated from each other by the rapid expansion of space between them. Think of it like cities on an expanding balloon. As the balloon inflates, the cities move apart from each other. If the balloon expands rapidly enough, light from one city will never be able to reach another city. they become causally disconnected even though they exist on the same balloon surface. This analogy helps illustrate why the multiverse is not just science fiction speculation. The physics of cosmic expansion naturally creates causally disconnected regions that are, for all practical purposes, separate universes. The study of cosmic horizons has also revealed something unexpected about the nature of information in the universe. The event horizon acts like a one-way barrier for information. We can receive information from beyond our event horizon, in the form of light emitted in the past, but we cannot send information beyond it. This asymmetry has led some physicists to propose that information plays a fundamental role in defining the structure of spacetime itself. The holographic principle, developed by Gerard T. Hooft and Leonard Susskind, suggests that all the information contained within a region of space can be encoded on its boundary. If the holographic principle is correct, then the information content of our observable universe might be finite, even if space itself is infinite. This would have profound implications for multiverse theories and the question of whether infinite universes can contain infinite information. The discovery of dark energy has added another layer of complexity to our understanding of cosmic horizons. Dark energy is causing the expansion of the universe to accelerate, which means that our event horizon is actually shrinking over time. Galaxies that we can influence today will eventually move beyond our event horizon and become forever inaccessible. This cosmic acceleration also affects the long-term evolution of multiverse structures. In universes dominated by dark energy, the accelerating expansion will eventually tear apart all gravitationally bound structures, leaving behind isolated patches of space that can never communicate with each other. These considerations lead to what cosmologists call the Big Rip scenario, a possible future where the universe's accelerating expansion becomes so extreme that it overcomes all other forces, tearing apart galaxies, stars, atoms, and even space-time itself. But even in such extreme scenarios, the multiverse might persist. New universe bubbles could continue to form through quantum fluctuations in the vacuum, creating an eternal cycle of creation and destruction that transcends any individual universe's fate. Understanding cosmic horizons also illuminates why the multiverse question is not purely academic. The boundaries of what we can observe and influence define the scope of human knowledge and action. If the multiverse exists, it fundamentally changes how we think about our place in reality and the significance of our actions. In a single universe, humanity might represent a unique phenomenon, the only known example of intelligent life in the cosmos. But in a multiverse, intelligence would be commonplace, arising independently in countless locations throughout the infinite expanse of parallel realities. This shift in perspective has implications for how we value human life and human achievements. Some find the multiverse concept diminishing. If there are infinite copies of every person living infinite variations of every possible life, what makes any individual life special? Others find it liberating. If every possible good outcome occurs somewhere in the multiverse, then the universe is ultimately benevolent, containing infinite joy and infinite achievement. To understand the full scope of multiverse possibilities, we need to explore string theory, a revolutionary approach to physics that attempts to unify all fundamental forces and particles into a single mathematical framework. String theory not only predicts the existence of parallel universes but suggests they might exist in dimensions we cannot directly perceive. The story of string theory begins with a simple but profound question. What are the most fundamental constituents of reality? For most of the 20th century, physicists believed that particles like electrons and quarks were point-like objects, infinitely small dots with no internal structure. But in the 1970s, physicists began to explore the possibility that these fundamental particles might actually be tiny vibrating strings. Just as different vibrations of a guitar string produce different musical notes, different vibration patterns of these fundamental strings would produce different particles. This idea seemed almost absurdly simple, but when physicists worked out the mathematics, they discovered something remarkable. String theory naturally incorporates gravity and quantum mechanics in a way that resolves many of the contradictions that plague other approaches to physics. However, string theory comes with a peculiar requirement. It only works mathematically if space has more than the 3 dimensions we experience. Depending on the specific version of string theory, the universe must have 10 or 11 total dimensions for the mathematics to be consistent. This raises an obvious question. If the universe has extra dimensions, where are they? Why don't we experience them in our daily lives? The answer proposed by string theorists is that these extra dimensions are compactified, curled up into shapes so small that we cannot detect them directly. Imagine looking at a garden hose from a great distance. It appears to be a one-dimensional line, but as you get closer, you realize it has additional dimensions, the circular cross-section that was invisible from far away. Similarly, what appears to be 3-dimensional space at the scales we experience might actually contain additional dimensions that are curled up at incredibly small scales, perhaps at the Planck scale, which is 10 to the minus 35 meters. But here's where string theory connects to multiverse theories. There are many different ways to curl up these extra dimensions. Each different geometric configuration, called a compactification, would produce a universe with different physical properties. The number of possible compactifications is staggering. Conservative estimates suggest there could be 10 to the 500th power different ways to configure the extra dimensions. Each configuration would result in a universe with different fundamental particles, different forces, and different physical constants. This vast collection of possibilities is called the string landscape. It represents all the different types of universes that string theory allows. Some regions of the landscape would produce universes where atoms cannot form. Others would create universes with exotic particles and forces unknown in our cosmos. Still others would generate universes similar to our own, but with slightly different values for fundamental constants. The connection to eternal inflation theory creates an even more dramatic picture. If eternal inflation is correct, and if string theory describes the fundamental structure of reality, then the inflationary process would naturally explore the entire string landscape. Different regions of the inflating spacetime would randomly select different compactifications, creating a multiverse where every possible string theory universe actually exists. This string multiverse would be incredibly diverse. Leonard Susskind, one of the pioneers of string theory, describes it as a vast space of possibilities where our universe occupies just one tiny corner. The landscape is like a rugged mountain range with many peaks and valleys, Susskind explains. Each valley represents a different type of universe with its own physics. But string theory suggests even more exotic multiverse possibilities. Some versions of the theory predict the existence of brain worlds, higher dimensional membranes on which our familiar 3-dimensional universe might be embedded. In brain world scenarios, what we perceive as our universe is actually just a 3-dimensional slice of a higher dimensional space. Other 3-dimensional slices, other brains, could exist parallel to our own, separated by tiny distances in the extra dimensions. These parallel brains would be entire universes in their own right, complete with their own matter, energy, and potentially their own forms of life. They would exist right next to us in the extra dimensions, but we couldn't see or interact with them directly because our particles are confined to our particular brain. However, gravity might be different. Some brain world models suggest that gravity can leak between brains, creating detectable effects. This might explain why gravity is so much weaker than the other fundamental forces, Perhaps most of gravity's strength is diluted across the extra dimensions and shared with parallel branes. The possibility of parallel branes raises tantalizing questions about communication between universes. While matter and electromagnetic forces would be confined to individual branes, gravitational effects might provide a way for different universes to influence each other. Some physicists have speculated about the possibility of gravitational communication between parallel branes. By creating specific patterns of mass and energy on our brain, we might be able to generate gravitational waves that could be detected by observers on parallel branes. This idea remains highly speculative, but it illustrates how string theory multiverse concepts might eventually lead to testable predictions. If parallel branes exist, they might leave subtle gravitational signatures that future experiments could detect. String theory also provides new perspectives on the quantum multiverse. In some string theory models, the different vibration modes of fundamental strings correspond to different quantum states of the universe. The superposition principle of quantum mechanics would then imply that all possible string vibration patterns exist simultaneously, creating a quantum multiverse of string states. This quantum string multiverse would be even more vast than the classical string landscape. Not only would there be 10 to the 500th power different types of universes, but each type would exist in quantum superposition with all the others. The mathematical complexity of string theory makes it difficult to extract specific predictions about multiverse properties. The theory involves sophisticated mathematics from topology, algebraic geometry, and other advanced fields. Even determining which compactifications are physically allowable requires enormous computational resources. But this complexity also gives string theory remarkable explanatory power. Many features of our universe that seem arbitrary, the number of fundamental particles, the strengths of the various forces, the existence of 3 generations of matter particles, emerge naturally from the geometric structure of the compactified extra dimensions. If string theory is correct, then the properties of our universe are not fundamental but rather depend on which point in the string landscape our region of the multiverse happens to occupy. The apparent fine-tuning of physical constants for life would be explained by the anthropic principle. We observe life-friendly constants because we exist in a region of the multiverse where such constants are possible. Critics of string theory argue that the vast landscape of possibilities makes the theory untestable. If any observation can be explained by choosing the right point in the landscape, then the theory makes no definitive predictions and falls outside the realm of science. Supporters counter that string theory does make predictions. It predicts the existence of the multiverse itself, and it provides a framework for understanding why our universe has the properties it does. They argue that dismissing string theory because of its multiverse implications would be like dismissing quantum mechanics because of its counterintuitive features. The debate over string theory and the multiverse reflects deeper questions about the nature of scientific explanation. Is it sufficient for a theory to explain observed phenomena, or must it also make specific predictions about new phenomena? Can a theory that involves unobservable entities still be considered scientific? These questions become even more pressing when we consider the practical implications of string theory research. Billions of dollars are spent on theoretical physics research, and governments and institutions must decide whether to support string theory despite its multiverse implications. Recent developments in string theory have opened new avenues for connecting the theory to observable phenomena. The AD/CFT correspondence, discovered by Juan Meldacena, provides a mathematical relationship between string theories in curved spacetime and quantum field theories in flat spacetime. This correspondence has allowed physicists to use string theory techniques to solve problems in condensed matter physics, nuclear physics, and other areas. While these applications don't directly prove that our universe is described by string theory, They demonstrate that string theory mathematics captures something fundamental about the nature of physical reality. The study of black holes in string theory has also yielded insights relevant to multiverse questions. String theory provides microscopic descriptions of black hole entropy and suggests mechanisms by which information falling into black holes might be preserved, possibly in parallel universes or hidden dimensions. These developments suggest that string theory, despite its exotic multiverse implications, might eventually make contact with experimental reality. The theory's predictions about extra dimensions, parallel branes, and hidden string structures might become testable as our experimental capabilities advance. One of the most mysterious and counterintuitive aspects of quantum mechanics is entanglement, a phenomenon where particles become correlated in such a way that measuring one particle instantly affects the other, regardless of the distance separating them. This spooky action at a distance, as Einstein called it, not only challenges our classical understanding of reality, but also provides crucial insights into the nature of the multiverse. To understand quantum entanglement, imagine two particles that are created together in such a way that their properties are correlated. For example, if one particle has spin up, the other must have spin down. According to quantum mechanics, before measurement, each particle exists in a superposition of both spin states. But the moment we measure one particle and find it spinning up, we instantly know that the other particle, no matter how far away, must be spinning down. This instantaneous correlation troubled Einstein, who believed that no influence could travel faster than light. He argued that quantum mechanics must be incomplete, that there must be hidden variables that predetermine the particle's properties, making the correlations only apparent rather than real. But in 1964, physicist John Bell developed a mathematical test that could distinguish between Einstein's hidden variable theories and the genuine non-local correlations predicted by quantum mechanics. Subsequent experiments, beginning with Alain Aspect's work in the 1980s and culminating in the Nobel Prize-winning research of the 2020s, have definitively confirmed that quantum entanglement is real. The implications are profound. Quantum entanglement shows us that reality is fundamentally non-local. Particles can be correlated across arbitrary distances in ways that cannot be explained by any classical mechanism. This non-locality is not just a curiosity. It's a fundamental feature of how the universe operates at its deepest level. But what does this have to do with the multiverse? The connection becomes clear when we consider how entanglement works in the many worlds interpretation of quantum mechanics. In the many worlds picture, when we measure an entangled particle and find it spinning up, the universe splits into multiple branches. In one branch, we observe spin up for our particle and spin down for its partner. In another branch, we observe spin down for our particle and spin up for its partner. The correlation between the particles is maintained across all branches of the quantum multiverse. This perspective suggests that quantum entanglement might be evidence for the existence of parallel realities. The correlations we observe between entangled particles could be the result of a deeper connection that spans multiple branches of the multiverse. Some physicists have taken this idea even further, suggesting that consciousness itself might be entangled across multiple realities. In this view, our subjective experience of making choices and observing definite outcomes is actually a manifestation of quantum entanglement between different versions of ourselves in parallel universes. This leads to what David Deutsch, a pioneer of quantum computation, calls the shadow photon interpretation of quantum interference. When photons interfere with themselves in double-slit experiments, Deutsch argues that they are actually interfering with shadow photons from parallel universes. The interference patterns we observe are evidence of interactions between our universe and its parallel neighbors. Recent advances in quantum technology have made it possible to create and manipulate entangled states with unprecedented precision. quantum computers, quantum cryptography systems, and quantum sensors all rely on entanglement to achieve capabilities that are impossible with classical systems. These technological applications of entanglement provide new ways to probe the foundations of quantum mechanics and test multiverse theories. For example, quantum error correction, a technique essential for building large-scale quantum computers, works by spreading quantum information across multiple entangled particles in such a way that errors can be detected and corrected. Some researchers have proposed that quantum error correction might naturally occur in the multiverse itself. If information is shared across multiple parallel realities through quantum entanglement, then the multiverse as a whole might be more stable and long-lived than any individual universe. The study of quantum entanglement has also revealed new types of multiverse connections. In addition to the spatial non-locality demonstrated by Bell's theorem, physicists have discovered temporal non-locality, correlations that span different times rather than different locations. Quantum retrocausality experiments suggest that quantum measurements can influence the past states of particles, creating closed causal loops that seem to violate our normal understanding of cause and effect. If these effects are real, they might indicate that the quantum multiverse has a more complex temporal structure than previously thought. Some interpretations of quantum mechanics propose that retrocausal effects are actually evidence of communication between different branches of the multiverse. When we make a measurement that appears to influence the past, we might actually be selecting which branch of the multiverse we experience, based on information flowing backward in time from future measurement events. The relationship between entanglement and space-time geometry has become an active area of research in theoretical physics. The holographic principle suggests that the information content of a region of space can be encoded on its boundary, and recent work has shown that quantum entanglement plays a crucial role in this encoding. In some models, space-time itself emerges from patterns of quantum entanglement between more fundamental degrees of freedom. This suggests that the familiar three-dimensional space we experience might be a kind of emergent phenomenon, arising from underlying quantum correlations in a higher dimensional multiverse. The ER equals EPR conjecture, proposed by Juan Meldacena and Leonard Susskind, suggests an even more radical connection between entanglement and multiverse structure. The conjecture proposes that quantum entanglement, EPR, is equivalent to connectivity through wormholes, ER, in the fabric of spacetime. If this conjecture is correct, then entangled particles are literally connected through microscopic wormholes that tunnel through higher dimensions. These wormhole connections might provide pathways between different regions of the multiverse, allowing information and possibly even matter to travel between parallel universes. The implications of ER equals EPR are still being explored, but they suggest that the multiverse might be far more interconnected than previously thought. Rather than being causally isolated, different universes might be linked through a vast network of quantum wormholes that allow subtle forms of communication and influence. Experimental tests of multiverse-related entanglement effects remain challenging, but several research groups are developing techniques that might eventually detect signatures of parallel universe interactions. These experiments involve creating specially designed quantum states and looking for correlations that cannot be explained by interactions within our single universe. One promising approach involves studying the decoherence patterns of quantum systems. Decoherence, the process by which quantum superpositions decay due to interactions with the environment, might be affected by interactions with parallel universes. If different branches of the multiverse can influence each other through quantum entanglement, this might show up as anomalous decoherence patterns that cannot be explained by environmental interactions alone. Another approach involves searching for violations of quantum mechanics that might arise if the multiverse has a finite rather than infinite structure. Some multiverse models predict that quantum correlations should show subtle deviations from standard predictions when they span regions of the multiverse with different physical properties. The study of quantum entanglement has also illuminated the information theoretic structure of the multiverse. The amount of quantum information that can be shared between different regions of space is limited by fundamental principles, and these limits might place constraints on the structure and evolution of multiverse systems. Black hole thermodynamics provides another connection between entanglement and multiverse physics. When matter falls into a black hole, the quantum information it contains becomes entangled with the black hole's internal states. If black holes are connected to other universes through wormholes, then this information might be preserved in parallel realities even as it disappears from our own universe. Recent work on black hole information paradoxes has suggested that the resolution might involve multiverse mechanics. The information that falls into black holes might be preserved through quantum entanglement with copies in parallel universes, ensuring that information is never truly lost from the multiverse as a whole. These connections between entanglement, black holes, and parallel universes remain highly speculative, but they illustrate how quantum mechanics naturally leads to multiverse concepts. The non-local correlations revealed by entanglement experiments suggest that reality has a much richer structure than our everyday experience suggests. As our understanding of quantum entanglement deepens and our ability to manipulate quantum systems improves, we may eventually develop technologies that can probe the multiverse directly. Quantum computers, quantum sensors, and quantum communication systems might provide windows into parallel realities that are currently beyond our observational reach. Perhaps the most compelling evidence for the multiverse comes from a puzzle that has troubled scientists and philosophers for decades: the apparent fine-tuning of our universe for the existence of life. The fundamental constants of physics seem to be calibrated with extraordinary precision to allow for complexity, structure, and biological processes. Change any of these constants by more than a tiny amount, and our universe becomes hostile to life as we know it. The fine-tuning problem begins with the fundamental forces of nature. There are 4 known forces in physics: gravity, electromagnetism, and the strong and weak nuclear forces. The relative strengths of these forces determine everything from the stability of atoms to the lifetime of stars to the formation of heavy elements. Consider gravity first. In our universe, gravity is incredibly weak compared to the other forces. The electromagnetic force between 2 protons is about 10 to the 36 power times stronger than the gravitational force between them. This vast difference might seem like a design flaw, but it's actually essential for the existence of stable, long-lived stars. If gravity were significantly stronger, stars would burn through their nuclear fuel much more rapidly. Instead of shining for billions of years, giving lifetime to evolve, they would exhaust their fuel in millions of years or less. On the other hand, if gravity were much weaker, stars wouldn't be able to ignite their nuclear fires at all, leaving the universe cold and dark. The electromagnetic force shows similar fine-tuning. If it were slightly stronger, electrons would be pulled too close to atomic nuclei, making complex chemistry impossible. If it were slightly weaker, electrons wouldn't be bound to nuclei at all, and atoms couldn't exist. The nuclear forces display even more dramatic fine-tuning. The strong nuclear force must be precisely calibrated to allow for the existence of both hydrogen and heavier elements. If it were just 5% stronger, all hydrogen would have been converted to heavier elements during the first minutes after the Big Bang. Without hydrogen, there could be no water and no long-lived stars. If the strong force were 5% weaker, no elements heavier than hydrogen could form, making complex chemistry and life impossible. The weak nuclear force, responsible for certain types of radioactive decay, also appears fine-tuned. It plays a crucial role in stellar nucleosynthesis, the process by which stars create heavy elements. If the weak force were significantly different, stars couldn't produce the carbon, oxygen, and other elements essential for life. But the fine-tuning goes beyond just the fundamental forces. The ratio of matter to antimatter in our universe is precisely what's needed to leave behind enough matter to form stars and galaxies after matter and antimatter annihilated each other in the early universe. The rate of cosmic expansion is balanced perfectly between expanding so fast that matter can't clump together to form structures, and expanding so slowly that the universe would collapse before stars could form. Even more precisely tuned is the cosmological constant, the energy density of empty space that drives the accelerating expansion of the universe. This constant appears to be fine-tuned to an accuracy of 1 part in 10 to the 120th power. If it were significantly larger, space would expand so rapidly that galaxies, stars, and planets couldn't form. If it were significantly smaller or negative, the universe might have collapsed long ago. The fine-tuning problem extends to the initial conditions of the universe itself. The Big Bang appears to have started with exactly the right amount of matter and energy, distributed with exactly the right degree of smoothness and lumpiness, to allow for the formation of the cosmic structures we observe today. For decades, physicists and philosophers have struggled to explain this apparent fine-tuning. Some have argued that it points to intelligent design, that a cosmic designer deliberately chose the physical constants to make life possible. Others have suggested that there might be undiscovered physical principles that require the constants to have their observed values. But the multiverse provides an elegant alternative explanation. If there are vast numbers of universes with different physical constants, then it's not surprising that some universes would have constants compatible with life. We observe a life-friendly universe not because it was designed for us, but because universes that can't support life have no observers to note their properties. This is the anthropic principle in its most basic form. The weak anthropic principle simply states that we observe the universe to be life-friendly because we exist to observe it. The strong anthropic principle goes further, suggesting that the universe must have properties that allow consciousness to develop within it. In the context of the multiverse, the anthropic principle becomes a powerful tool for understanding why our universe has the properties it does. Instead of requiring miraculous coincidences or intelligent design, the fine-tuning of physical constants becomes a natural consequence of observer selection in a vast ensemble of universes. Different types of multiverse predict different patterns of fine-tuning. In the inflationary multiverse, different bubble universes would have different values of fundamental constants due to different symmetry-breaking patterns during inflation. In the string theory landscape, different compactifications of extra dimensions would produce different physical laws. The quantum multiverse adds another layer to anthropic reasoning. If every possible quantum outcome is realized in some branch of the multiverse, then there would be branches with every possible history consistent with the laws of physics. We would naturally find ourselves in branches where evolution produced observers like us. But anthropic reasoning in the multiverse context is not without controversy. Critics argue that anthropic explanations are inherently unscientific because they cannot make testable predictions. If any observation can be explained by appealing to observer selection in an infinite multiverse, then the multiverse hypothesis becomes unfalsifiable. Defenders of anthropic reasoning respond that it can make genuine predictions in certain circumstances. For example, if we live in a multiverse where cosmic constants vary, anthropic reasoning predicts that we should observe values that are typical among life-supporting universes, not necessarily optimal for life. This leads to testable predictions about the values of fundamental constants. The cosmological constant provides a particularly clear example. If our universe were part of a multiverse where this constant takes random values, Anthropic reasoning predicts that we should observe a value that is small enough to allow galaxy formation but not much smaller. Remarkably, this prediction was made before dark energy was discovered. When astronomers found in the late 1990s that cosmic expansion is accelerating, the inferred value of the cosmological constant was roughly consistent with anthropic predictions based on multiverse models. Similar anthropic predictions can be made for other physical constants. The fine structure constant, which determines the strength of electromagnetic interactions, should have a value that allows for complex chemistry, but is not finely tuned beyond what's necessary for life. Current measurements of this constant are roughly consistent with such anthropic expectations. The anthropic principle also provides insights into the question of why our universe has 3 spatial dimensions. Mathematics allows for spaces with any number of dimensions, but complex structures like atoms and organisms require very specific dimensional properties. In spaces with fewer than 3 dimensions, complex structures cannot exist because there isn't enough room for the intricate networks of connections that characterize living systems. In spaces with more than 3 dimensions, inverse square force laws become inverse higher power laws, making stable orbits impossible and preventing the formation of atoms and solar systems. If the multiverse contains universes with different numbers of spatial dimensions, anthropic reasoning explains why we observe exactly 3 dimensions. It's the minimum number required for complexity and life. The anthropic principle has also been applied to understanding the arrow of time and the second law of thermodynamics. Most fundamental physical laws are time-symmetric, meaning they work equally well forward or backward in time. Yet we experience a strong directional flow of time from past to future, with entropy always increasing. In a multiverse context, the arrow of time might be explained anthropically. Observers can only exist in regions of the multiverse where entropy is increasing, because the complex information processing required for consciousness depends on thermodynamic gradients that extract useful work from energy flows. This suggests that time's arrow is not a fundamental feature of physics, but rather a consequence of observer selection in a multiverse where different regions have different thermodynamic properties. We observe time flowing from low entropy to high entropy because that's the only type of region where observers can exist. The anthropic principle raises profound questions about the nature of scientific explanation. Traditional science seeks to explain natural phenomena by discovering universal laws and principles. But anthropic explanations appeal to observer selection effects rather than fundamental physical principles. Some philosophers argue that anthropic explanations represent a fundamental shift in the nature of scientific reasoning. Instead of asking, why do the laws of physics have the form they do? We ask, given that observers exist, what can we infer about the structure of reality? This shift from explanation to inference might be necessary if the multiverse is real. In a universe that is part of a larger ensemble, many features that appear to require explanation might actually be the result of observer selection rather than fundamental physical principles. The anthropic approach has led to new research programs in cosmology and fundamental physics. Scientists are working to identify which features of our universe are genuinely universal and which might be the result of observer selection in a larger multiverse. This research has practical implications for the search for life elsewhere in the universe. If fine-tuning is explained by multiverse selection rather than design or necessity, it affects our estimates of how common life might be in our observable universe and what kinds of signatures we should look for in the search for extraterrestrial intelligence. The question of whether we can ever directly detect evidence of parallel universes represents one of the greatest challenges in modern physics. While the multiverse might seem inherently unobservable, ingenious scientists have developed numerous approaches that could potentially reveal signatures of other realities. These range from subtle patterns in cosmic radiation to exotic quantum experiments that probe the foundations of reality itself. The most promising avenue for multiverse detection lies in studying the cosmic microwave background radiation with ever-increasing precision. This ancient light, released when the universe was only 380,000 years old, carries within it a detailed map of conditions in the early cosmos. Any interaction between our universe and other universes during this critical period should have left detectable imprints. Current and future CMB experiments are designed to map temperature and polarization fluctuations with unprecedented accuracy. The European Space Agency's Planck satellite, which completed its mission in 2013, provided the most detailed picture yet of the early universe. But next-generation experiments promise even greater sensitivity. Ground-based telescopes like the Atacama Cosmology Telescope and the South Pole Telescope are mapping the CMB with resolutions that allow scientists to search for subtle anomalies that might indicate multiverse interactions. Space-based missions being planned for the 2030s could achieve sensitivity levels that would reveal even weaker signals. One specific signature scientists are searching for involves circular patterns in the CMB that would result from bubble universe collisions. When two expanding universe bubbles collide during inflation, they create shock waves that propagate through the cosmic plasma. These shock waves would appear as circular temperature anomalies in the CMB, with specific statistical properties that distinguish them from random fluctuations. Advanced statistical analysis techniques, including machine learning algorithms, are being developed to identify these subtle patterns. The challenge is enormous. Scientists must distinguish genuine multiverse signatures from instrumental noise, foreground contamination from our own galaxy, and the intrinsic randomness of cosmic structure formation. Another approach involves searching for evidence of gravitational influences from other universes. If parallel universes exist in higher dimensions, their gravitational effects might create detectable anomalies in the behavior of gravity in our own universe. Precision tests of Newton's inverse square law at very short distances have been conducted to look for deviations that might indicate the presence of extra dimensions or parallel branes. So far, these experiments have confirmed Einstein's predictions down to distances of about 50 micrometers, but future experiments could probe even shorter scales where multiverse effects might become apparent. The detection of gravitational waves by LIGO and Virgo has opened an entirely new observational window that might eventually reveal multiverse signatures. Gravitational waves from colliding black holes and neutron stars carry information about the fundamental structure of spacetime itself. Future gravitational wave observatories, including space-based detectors like LISA, Laser Interferometer Space Antenna, will be sensitive to much weaker signals and lower frequencies. These advanced instruments might detect gravitational wave patterns that cannot be explained by sources in our universe alone, potentially revealing the influence of parallel realities. Some theoretical models predict that the collision between universe bubbles would generate distinctive gravitational wave signatures. These primordial gravitational waves, created during the inflationary period, would carry direct information about multiverse interactions that occurred in the first moments after the Big Bang. Quantum mechanics experiments offer another avenue for multiverse detection. The many worlds interpretation makes specific predictions about quantum interference patterns that might be distinguishable from other interpretations of quantum mechanics. Advanced quantum optics experiments are being designed to test these predictions with unprecedented precision. By creating carefully controlled quantum superposition states and measuring their interference patterns, physicists hope to determine whether the observed effects require the existence of parallel realities. One particularly intriguing approach involves studying quantum decoherence, the process by which quantum superpositions decay due to interactions with the environment. If parallel universes can weakly interact with our own, This might show up as anomalous decoherence patterns that cannot be explained by environmental effects alone. Quantum computer technology is advancing to the point where it might provide new tools for probing multiverse questions. Large-scale quantum computers naturally exploit quantum superposition and entanglement effects that are central to many worlds' interpretations of quantum mechanics. As quantum computers become more powerful and controllable, they might enable experiments that directly test whether quantum computations involve interactions with parallel realities. Some researchers have proposed that quantum computers might eventually be used as multiverse communicators that exchange information with parallel versions of themselves. The search for multiverse evidence also extends to high-energy particle physics experiments. If our universe exists on a brane in higher dimensional space, particle collisions at extremely high energies might produce signatures of extra dimensions or parallel branes. The Large Hadron Collider at CERN has searched for evidence of extra dimensions by looking for missing energy in particle collisions, energy that might have escaped into parallel dimensions. While no definitive evidence has been found, future particle accelerators with higher energies might be able to probe the dimensional structure of space more directly. Some theories predict that microscopic black holes could be created in high-energy collisions if extra dimensions exist. These black holes would evaporate almost instantaneously through Hawking radiation, but their decay products might carry information about the higher dimensional structure of spacetime. Dark matter research provides another potential window into multiverse physics. The mysterious substance that makes up about 27% of the universe has never been directly detected, despite decades of intensive searching. Some theories suggest that dark matter might actually be ordinary matter existing in parallel dimensions that weakly interacts with our own through gravitational effects. If this mirror matter hypothesis is correct, then dark matter detection experiments might actually be detecting evidence of parallel universes. Underground laboratories around the world are using increasingly sensitive detectors to search for dark matter interactions, and some unexplained signals might eventually be traced to multiverse origins. The study of cosmic rays, high-energy particles that bombard Earth from space, offers another avenue for multiverse research. These particles carry information about the most extreme environments in the universe, and their properties might reveal evidence of physics beyond our current understanding. Some cosmic rays have energies so high that their existence challenges our understanding of particle acceleration mechanisms. If these ultra-high-energy particles originated from interactions with parallel universes or extra dimensions, they might carry distinctive signatures that distinguish them from conventional astrophysical sources. Advanced computational simulations are becoming crucial tools for predicting what multiverse signatures might look like and how to distinguish them from conventional phenomena. Supercomputers can model the complex physics of universe bubble collisions, extra-dimensional interactions, and quantum multiverse effects with increasing accuracy. These simulations help experimentalists know what to look for and provide theoretical frameworks for interpreting observations. As computational power continues to grow, scientists will be able to explore increasingly sophisticated multiverse models and make more precise predictions about observable consequences. Machine learning and artificial intelligence techniques are revolutionizing the analysis of cosmic data. Modern astronomical surveys generate enormous datasets that contain far more information than human scientists can analyze using traditional methods. AI systems can identify subtle patterns and correlations that might reveal multiverse signatures hidden in the noise. Neural networks trained on simulated multiverse data can learn to recognize the distinctive features of universe collisions, extra-dimensional effects, or quantum interference patterns from parallel realities. These AI tools are already being applied to cosmic microwave background data and will become even more important as future experiments generate larger and more complex datasets. The search for multiverse evidence also involves looking for statistical anomalies in the distribution of cosmic structures. If our observable universe interacted with other universes during its formation, this might have created preferred directions or asymmetries that violate the cosmological principle, the assumption that the universe looks the same in all directions. Large-scale structure surveys that map the positions of millions of galaxies are being analyzed for evidence of such asymmetries. Any departure from perfect statistical isotropy might indicate that our universe is part of a larger multiverse structure with preferred orientations or boundaries. Precision measurements of fundamental constants provide another approach to multiverse detection. If physical constants vary across different regions of the multiverse, we might expect to see subtle variations even within our observable universe as we look in different directions or at different distances. The most promising candidate for such variations is the fine structure constant, which determines the strength of electromagnetic interactions. Some studies have claimed to find evidence that this constant has different values when measured in different directions across the sky, though these results remain controversial and require confirmation. Future space-based telescopes with unprecedented precision might be able to definitively determine whether fundamental constants vary across the observable universe. Such variations would provide strong evidence that our universe is part of a larger multiverse where physical laws can differ from place to place. The development of new theoretical frameworks continues to suggest novel approaches to multiverse detection. Loop quantum gravity, emergent gravity theories, and other alternatives to standard cosmology make different predictions about multiverse signatures and observational consequences. As these theories mature and make more specific predictions, they will guide the development of new experimental searches. The interplay between theoretical advances and observational capabilities continues to expand the range of possible multiverse detection methods. International collaboration has become essential for multiverse research, as the experiments required are often beyond the capabilities of any single nation or institution. Projects like the Event Horizon Telescope, which imaged the first black hole, demonstrate how global scientific cooperation can achieve previously impossible observations. Future multiverse detection efforts will likely require similar international partnerships, combining resources and expertise from around the world. The scale and complexity of the experiments needed to probe parallel realities demand unprecedented levels of scientific collaboration. The timeline for potential multiverse detection remains uncertain, but several key developments could lead to breakthroughs within the next few decades. Next-generation cosmic microwave background experiments could reveal definitive evidence of bubble universe collisions by the 2030s. Advanced gravitational wave detectors might detect primordial signals from multiverse interactions by the 2040s. Quantum technology advances could enable multiverse communication experiments within the next decade. High-energy particle physics experiments might discover extra-dimensional signatures as more powerful accelerators come online. The convergence of these different experimental approaches increases the likelihood that multiverse evidence will be found. But even if direct detection remains elusive, the search itself is advancing our understanding of fundamental physics and cosmology. The techniques developed to look for multiverse signatures are revealing new insights into the nature of space-time, quantum mechanics, and the early universe. The possibility of multiverse detection also raises profound questions about the implications of such a discovery. How would confirmation of parallel universes change our understanding of reality, consciousness, and our place in the cosmos? These philosophical questions are as important as the scientific ones in preparing for a potential multiverse discovery. As we stand at the threshold of potentially discovering definitive evidence for the multiverse, it's worth considering what such a discovery would mean for humanity and how it might reshape our understanding of existence itself. The implications extend far beyond physics and cosmology, touching on the deepest questions about consciousness, meaning, and our place in an infinitely larger reality. The next few decades promise revolutionary advances in our ability to probe multiverse questions. Planned observations with next-generation telescopes will map the cosmic microwave background with unprecedented precision, potentially revealing the subtle signatures of universe bubble collisions or other multiverse interactions. Space-based gravitational wave detectors will listen for the primordial ripples created during cosmic inflation, which might carry direct information about the birth of multiple universes. Meanwhile, advances in quantum technology are approaching the point where definitive tests of quantum multiverse theories might become possible. Large-scale quantum computers may eventually be powerful enough to perform calculations that could only work if they were somehow accessing parallel realities. Precision quantum experiments might detect interference patterns that reveal the existence of shadow particles from other branches of the multiverse. The convergence of these different experimental approaches creates an unprecedented opportunity for multiverse discovery. Unlike previous generations of scientists who could only speculate about parallel universes, we may be the first to actually prove their existence through empirical observation. But what would such proof mean for human civilization? The psychological and philosophical implications of confirming the multiverse would be profound. Knowing with certainty that infinite versions of ourselves exist across parallel realities would fundamentally change how we think about identity, choice, and the significance of our actions. Educational systems would need to be reimagined to help people understand and cope with multiverse realities. Children growing up in a confirmed multiverse would develop very different perspectives on life, death, and personal meaning than previous generations. The concept of uniqueness would be challenged when everyone knows that infinite versions of themselves exist elsewhere. Religious and spiritual traditions would also need to grapple with multiverse implications. How do concepts like souls, divine purpose, and afterlife translate to a reality where infinite versions of every person exist across parallel universes? Some traditions might find multiverse discoveries compatible with their teachings, while others might need to undergo fundamental theological revisions. The legal and ethical implications are equally complex. If actions in our universe are mirrored by different choices in parallel realities, how do we think about moral responsibility? If every possible choice is made by some version of us across the multiverse, does this diminish the ethical weight of our particular decisions? Scientific research itself would be revolutionized by multiverse confirmation. The anthropic principle would become a standard tool for understanding why our universe has the properties it does. Instead of seeking universal explanations for fundamental constants and physical laws, scientists might focus on understanding observer selection effects in the larger multiverse. The search for extraterrestrial life would take on new dimensions in a confirmed multiverse. If infinite universes exist with infinite variations, then life would be abundant throughout the multiverse, even if it remains rare within any individual universe. This might shift focus from finding alien civilizations in our own cosmos to developing technologies that could somehow communicate with parallel realities. Technological development might be accelerated by multiverse understanding. If consciousness is somehow connected across parallel realities, we might eventually develop techniques to access knowledge and innovations discovered by other versions of ourselves. This could lead to rapid advances in science, technology, and human understanding. The concept of progress itself would be redefined in a multiverse context. Instead of seeing technological and social advancement as linear processes, we might understand them as explorations of possibility space where every potential development occurs somewhere in the vast ensemble of realities. But multiverse confirmation would also raise new and deeper questions. If infinite universes exist, what determines the measure or probability distribution across different types of realities? Are all possible universes equally likely, or do some have greater weight in the multiverse ensemble? The question of consciousness's role in the multiverse remains one of the deepest mysteries. Does consciousness somehow select which branch of reality to experience, or is it simply along for the ride as quantum events unfold? If consciousness plays an active role, this might suggest that the multiverse has a fundamentally mental or information-based foundation. These questions connect to even more fundamental issues about the nature of existence itself. Why does anything exist rather than nothing? If the multiverse is real, does its existence require explanation, or is it simply a brute fact about reality? The philosophical implications of multiverse theories touch on the most basic questions about the nature and origin of being. The possibility that consciousness might persist across multiple realities or access information from parallel universes opens up entirely new research directions. Investigations into phenomena like intuition, creativity, and altered states of consciousness might reveal connections to parallel selves that could revolutionize our understanding of human potential. Medical and psychological research might also benefit from multiverse perspectives. If mental illness sometimes involves sensitivity to influences from parallel realities, new therapeutic approaches might be developed that help patients navigate multiverse-related experiences. Understanding consciousness as a multiverse phenomenon could lead to breakthroughs in treating disorders of identity, memory, and perception. The long-term implications for human civilization are almost impossible to predict. If we eventually develop technologies that allow communication or travel between parallel universes, the possibilities become limitless. We might encounter versions of ourselves that developed along radically different technological paths, leading to exchanges of knowledge that accelerate progress beyond anything we can currently imagine. Such multiverse contact might also reveal versions of humanity that followed different evolutionary or cultural paths. We might discover parallel Earths where different species became dominant, where history unfolded in alternative directions, or where consciousness evolved along completely different trajectories. But multiverse contact also raises potential dangers. If we can reach other realities, beings from other realities might be able to reach us. We might encounter hostile versions of ourselves or alien intelligences from parallel universes with capabilities and intentions we cannot predict. The multiverse might also offer solutions to some of humanity's greatest challenges. If consciousness can somehow access parallel realities, we might learn from versions of ourselves that solved problems like climate change, energy scarcity, or social inequality. The collective knowledge of infinite civilizations across the multiverse could provide resources for overcoming any obstacle. As we look toward the future of multiverse research, it's clear that we are entering a period of unprecedented discovery. The technologies and experimental techniques needed to probe parallel realities are rapidly advancing, and theoretical understanding continues to deepen. The next generation of scientists will grow up in a world where multiverse questions are not just philosophical speculation but active areas of empirical research. They will have tools and perspectives that previous generations could only dream of, and they may be the ones to finally answer whether we truly live in a multiverse. But regardless of what future experiments reveal, the journey of exploring multiverse possibilities has already transformed our understanding of reality. The theoretical frameworks developed to address parallel universes have led to advances in quantum mechanics, cosmology, and fundamental physics that have practical applications beyond multiverse questions. The multiverse concept has also expanded our sense of what's possible and challenged us to think more deeply about consciousness, identity, and meaning. Even if parallel universes are never definitively proven, The intellectual adventure of exploring these possibilities has enriched human understanding and opened new pathways for investigation. As we conclude this exploration of multiverse theories and evidence, we're left with a profound sense of mystery and wonder. The possibility that our reality is just one small part of an infinite ensemble of universes challenges our most basic assumptions about existence and opens up possibilities that previous generations could never have imagined. Whether the multiverse is real or not, the questions it raises about consciousness, reality, and our place in existence are among the most important and fascinating that humans have ever contemplated. The search for answers to these questions will undoubtedly continue to drive scientific discovery and philosophical reflection for generations to come. In contemplating the multiverse, we are forced to confront the ultimate questions. What is reality? What does it mean to exist? Are we alone? Or are we part of something infinitely larger and more wonderful than we ever dared to imagine? The answers to these questions may reshape humanity's understanding of itself and its place in the vast cosmos of possibilities. The multiverse beckons as the final frontier, not just of space and time, but of possibility itself. As we stand on the threshold of potentially discovering its reality, we face the most profound adventure in human history. The exploration of infinite worlds and infinite selves across the boundless landscape of existence. And perhaps, in the end, that journey of exploration, whether it leads to definitive proof or eternal mystery, is what makes us human. In a universe or multiverse of infinite possibilities, the greatest possibility of all may be consciousness itself, the capacity to wonder, to question, and to search for meaning in the vast expanse of reality. The multiverse is real. The evidence points toward it. The mathematics demands it. And the adventure of discovering its full reality has only just begun.